Liquid and glass thermometer is a very common type of thermometer, and through which we can easily calculate the temperature of any any part of the system. Most of the time mercury is used, and the basic the reason behind is that mercury is not a very wetting liquid. uh, so it has dominance in intermolecular forces, and definitely it does not have adhesive forces, the forces of the molecule with the wall of the glass. So and on the other hand, it will give you a very good expansion with the increment of temperature. Its density varies linearly with the increment or decrement of the temperature. And definitely it is very clearly transfers, and you can easily read up. If the glass is transparent, you can easily check out there is no bubble trapped out in this type of liquid. So it's very ideal liquid for using in order to calculate or to work as a gauge liquid. The main thing is that the range of this type of thermometer is around -30 degrees to 800 Fahrenheit, and if you will convert it into degrees Celsius, is around -35 to +45 degrees centigrade. And you can see clearly that the mercury has a freezing point of -38 Fahrenheit, or if you will convert that the same temperature in degrees Celsius, so it will have the same value. If we discuss about the main drawbacks of using this type of thermometer, so certainly mercury is a toxic material, and if you are dealing with the food type of material, so it's quite you need to take account a lot of hazard studies in order to make sure that it does not mix up or there is no breakage occur within your temperature measuring device, and there is no mixing will be carried out within the system. So as we know that this type of thermometer are made up of glass, so they cannot bear a lot of pressure and expansion, even if there is sudden increment in the temperature and decrement in the temperature within the process. So the glass material can break up. It does not bears this type of thermal shocks as compared to other metal materials. So we can use this in laboratory scale. We can use it in pilot level even scale, but again it's very typical to attach these type of liquid with in order to transmit electrical signal. Most of the time we are interested to develop the sensor or measuring device which transmit your signal from your plant area to your control room. And there are two type of signals most of the time used in the industry. One is the pneumatic signal, and the second is electrical signal. If we talk about the food engineering, so the input signals are most oftenly coming in electrical signals. So mercury has a lot of properties, and if we draw back, these are the drawbacks in fact. And if we analyze this type of measuring devices in cost wise, so definitely they are quite inexpensive, very good accurate, because of the linearity or linearly increment of the volume of the mercury along a particular length. But again, they cannot bear up a lot of pressure, but the maximum range that they can be used in order to calculate out operating range, like minus 300 to 1000 degree Fahrenheit, which is a very huge range. But again, the main limitations is they are sensitive. They cannot be used in a manner that you can get the input signal from them. So these are the certain drawbacks of these type of temperature measuring devices. So this is a very common type of thermometer, and even I believe that you have seen it in your home as well. So they are domestic. They are abundantly used in domestic purpose for checking the room temperature or for checking the relative humidity of your environment even, and body temperature even. And this type of thermometer even used in the industry, okay, and the basic purpose of that is they give you accurate reading of dry bulb temperature and well bulb temperature, and they are placed in different part of your industry. Like if you are working, if you are producing a packaging material, so packaging material definitely required a dehumid atmosphere. So wherever the processing is going on, so the film, the packaging material in fact will after molding process, like extrusion, and then the extruder pump the material. Like most of the time we use polypropylene or polyethylene type of polymers. In the extruder pump these liquid into the die, and die just shaped it out into the desired shape, and then they come across direct to the atmosphere where their temperature are higher. At the die, most of the material vary. It definitely depends upon which type of material. If you are producing polyethylene packaging material, so for that material the temperature at die is around 190 degrees centigrade to 210 degrees centigrade. And if you are making polypropylene film, so certainly it is it has a temperature. The temperature in the die is around 220 to 250 degrees Celsius. So but after that, the film come across direct to the atmosphere of your definitely the plant area site. And most of the packaging industries are indoor industries, like they are in central AC conditions, as their the film required dehumidified atmosphere, as I have explained you before. So that's why you are supposed to monitor the humidity level of this type of sensitive area of your industry, like what is the relative humidity is going on in indoor processing area. Maybe if there is something, or definitely there are equipments like cooling towers and other equipments are used in the industry to sink down their heat energy into the atmosphere, and their efficiency is also very much depend on the relative humidity. So to monitor the relative humidity at the near to the cooling tower, what is going on, so you can place this type of thermometer in order to assess the dry bulb temperature and wet bulb temperature. Once you know both of the temperature, you can easily calculate the relative humidity. So that's why it's not like that they cannot be used in the industry at all. So definitely they have certain applications, and the basic reason is that they give you very accurate reading. In fact, the margin of error is very much minimum. These are the certain parts of any glass thermometer. Like definitely it has a certain scale calibrated on the glass. Then we have a bore. Bore is the confined place where the mercury can move, expand or contract according to the temperature conditions. Then we have lens front capillary tube, okay, which is present here. Then we have a glass column, which is made here, and the bulb, and we have to attach this bulb with the body, and by attaching that, this expansion took place, and from this calibrated scale we can easily calculate what is the temperature, how much temperature increases with this change or how much temperature decreases with the change. So this is another type of thermometer, but again it has more safety protections like protective case and socket that you can attach it in the pipeline as well. But again it will give you the analog reading, and it does not transmit the digital reading of that through this temperature gauge. Then we have bimetallic strip thermometers. Bimetallic strip thermometer is also use the thermal expansion, but you attach two strips of solids. In the previous thermometer we utilize the thermal expansion within the liquid, and on the other hand here we connect two type of solid materials, and on the changing the temperature, their contraction and expansion will give you the reading of how much temperature increases or decreases through the calibrated scale. But they are relatively inaccurate. Temperature measuring devices which is slow to respond, because the conduction process is a bit slower as compared to convection or how the radiation. So in convection the temperature reading will come up so quickly. On the other hand, in bimetallic it's work on conduction. So in solids heat transmitted, but it took certain times. The device is low cost and extensively used. In some of time we have to use on and off type of applications, like electric very abundantly use electric kettles at your homes. So they utilize this type of bimetallic strips. There what happen, you place certain amount of water in the kettle and plug it on the socket and switch on that electric kettle. So the electrical element is converting the electrical energy into the heat, okay, and that heat is utilizing in order to heat up the water. When the water start to boil, and I believe you have experienced this, that after expanding boiling temperature, when you have reached that particular temperature, and after spending certain time after that, the electric kettle automatically turned off. So this is the response time of bimetallic strip thermometer, that it took certain time in order to reach the 100 degrees centigrade. Okay, actually, although in the process you have reached 200 degrees centigrade way before. Okay, after 20 to 25 seconds, or maybe below than like 15 to 10 seconds. After that it will reflect you the same reading. So in the process, like you have a tolerance level, like you have to run your process within the range of 200 to 210 degrees centigrade. So for that purpose you can use this type of thermometer to respond on. Like it will turn off when the 210 degrees centigrade reach within your process, and it will respond to turn off the heating source. The heating source may be depend upon the process. Most of the time you are using a fluid in order to heat up any material, or maybe most of the time, if like I have give you the example of production of polypropylene film and polyethylene films. So in extruder process, the electrical heaters are abundantly used to heat up these type of material, or to polymerize them. So you can use these bimetallic strip thermometer over there, because in electrical heater they will work on just on and off working. Like if you are your heating source is a fluid, so you can install a control valve over there, and by regulating the flow rate of, like if you are using a steam for providing heat to any in any heat exchanger, so you may vary their flow rates in order to control the temperature. But in electrical heater they only respond and on and off. There is no certain type of changing in the voltages or changing in the heat amount of that. So they can be used in order to control. You will, I believe, study in the next semester in process control about that they can also be attached with PID controllers or any other logics in order to control your process so efficiently. But the main idea is quite similar, that they work only on and off type of controlling system. Another application of this type of thermometers are analog type display. Like at the beginning of the lecture I have told you that nowadays every unit of food industry will run automatically, and everything is coming on your single PC. Okay, the software, I mean the controlling software will display you the whole parameter of your process, whether your process is so huge or whether your process is so small. But there are certain field readings you need to attach on the same position where you have attached the sensors for your the sensors who are providing inputs values to your controlling system. So you can correlate your controlling system values with the field values in order to optimize that, whether your transmitter working properly or not, or whether your field gauge is working properly or not. So they are abundantly used in for analog readings, for analog indications, which is you simply called as the industrial field reading or plant reading. For that you have to go to the equipment, and you have to see the same way that what is the reading of that particular thermostrip thermometer is coming. Mm, so what is the main working principle of this type of thermometer? As we know that every metal has have a unique coefficient of expansion, and when you attach it with another metal, so one expand more, on the other hand the next expand lesser than the first one. So by this behavior, what happened, the strip start to bend itself. Okay, most of the time we use brass and invar, which is a alloy of copper and nickel, and we join it together with the fixed points, and when they expand, so certainly they cause certain bending behavior in their strips. When you're using a straight bimetallic strip, an important calculation to determine the movement of free end of the strip is given by the formula written here, like D is equals to, they will rotate around diameter, and which can be easily determined by 3AA minus AB T2 minus T1 L square over T. So here D is the deflection, okay. AA is the linear coefficient of expansion and of metal A. AB is the coefficient of expansion of metal B. T1 is the low temperature. T2 is actually the elevated, or you may say that the final temperature, and L is simply the length of the element, and T is the thickness of these elements. So its geometry is something like that, and you can clearly see here there is a banded strips attached here, and once they start to bend, they twisted here. On the other hand, their twisting behavior observed, which is attached with the pointer, and there is a calibrated scale, okay, and calibrated according to temperature properly, but they certainly required certain time to give you an accurate reading. So this whole part of bimetallic strip thermometer should be attached into the process, okay, and it will simply come, this is the off part of the process, although this orange part is completely should into submerged with the process, okay, so that it will give you a very accurate reading. If certain part is not attached with your process and properly not into your process, so certainly it will deviate the temperature a lot. These are certain parts of bimetallic strip, like bimetallic connection of rod. This is the stem complete, okay, on which it is confined. This bimetallic strip is confined. Bimetallic connected pin, okay, this is complete part of bimetallic strip. After that, there is the arrangement to calibrate the scale in a manner that you can see. This is the pointer, sliding bearing, okay, so that it can rotate freely. Helical bimetallic strip is also attached here. So these are the certain part of bimetallic strip. Then I have a very simple video in order to explain you that how bimetallic strip work. So this is the complete casing, and you can see here this is the twisted strip, bimetallic strip in fact, which is attached throughout the column, and it will expand and contract accordingly. And when they expand and contract, they will there is a shaft attached with this, which move upward and downward, and on which there are gears attached with them, so that they will respond accordingly, as you can see here. Okay, they can expand and contract in similar way, that when they expand, the rod move upward and downward with their respective timing. So, and in that way they are calibrated. So this is the very simple working principle of bimetallic strip thermometers, but you need to take account their main functions, their applications. They can be used to transport your signal to the control room, and in order to control your equipment temperature. But most of the time in the industry we utilize them in order to control when we have some on and off logics of controlling system, and on the they can be used in order to control a system where the tolerance level is higher. Okay, if you are supposed to control a process very sensitively, so there you cannot afford to attach this type of thermometer. And it is also depends upon the source of your heat as well, that if you are using electrical heaters, so you can easily use them in order to control them, as they are quite inexpensive, and they are simple to use, but their accuracy is not very much good. Then we have a very simple numerical in which a straight bimetallic strip of 25 centimeter long and 1.4 mm thick is made of copper and in wear. Okay, and has one end fixed. How much will the free end of the strip deflect if the temperature changes is equals to 18 degree Fahrenheit? So in this numerical, they have provided us these values, like the length of the strip is 25 centimeter, T2 minus T1 is 18 degree Fahrenheit. Okay, they have provided us a change in temperature values in degree Fahrenheit. The thickness of the strip is 1.4 mm. On the other hand, the coefficient of linear expansion, thermal expansion for copper is 9.4 into 10 raised to power minus 6 per degree Fahrenheit, and for the alloy is 0.67 into 10 raised to power minus 6. But here these two values you need to take from the table. The formula is of the deflection is simply equals to 3 alpha C minus alpha N. Okay, T2 minus T1 L square, and we have over T. So we just need to put all these values in our this formula. So it will be something like 3 multiplied by 9.4 minus 0.67. Both have the same powers, so you just took the common here. Okay, then multiply by T2 minus T1 is 18. L is actually the length of the S-strip, and certainly we will convert it into meters. So just divide it, that value with the 100, we will get 0.25. Okay, so this will be the square of 0.25, and over. If I will just convert that one into meters, just need to add the m value, which is 1.4 into 10 raised to power minus 3 with no sign. So now just the calculations are remaining, like 3 multiplied by 9.4 minus 0.67 bracket close multiplied by 10 raised to power of minus 6 multiplied by 18 multiplied by 0.25, and let's take the square of this value, and over 1.4 into 10 raised to power minus 3. So the answer is around 0.02104 meters, and if I will convert it into centimeters, so it will be around 2.104 centimeter will be the increment, and it will deflect that much amount. Then we have another type of temperature measuring device, pressure spring thermometer. At the beginning of this course, you have, I think, covered all the pressure gauges which can be used in order to, even pressure transmitters which can be used in order to transmit the input values for the input pressure values from the field to your control room, and certainly the gauges as well, which give you the field readings. So we will utilize the linear expansion property and linear volume expansion and volume property of the fluids in order to calculate them with the same way, like the increment in the length will apply the pressure on the gauge, and the upper part of the gauge will be quite similar what you have learned in the pressure gauges. So it is a combination of both of them, and in that way you can easily calculate the temperature instead of pressure by these type of temperature measuring devices. So pressure spring thermometers are normally used and they are quite different than what you have studied in glass or bimetallic devices, which give you the reading at a point and detect point of detection. Like bimetallic strip is used to just to monitor that your temperature is reached up to that much mark, but this is not the scenario in pressure spring thermometers. These devices has metal bulb made up of low coefficient of expansion metals along with a long metal narrow bore tube. Okay, the geometry will be we will discuss in later on. Both contain materials with a high coefficient of expansion. The bulb is monitoring the point, and then it is attached with a burden spring pressure gauge, and so that you will record your readings, or it may change your actuator positioner, and may use in order to transmit the electrical signal as well to your control room. As the temperature in the bulb increases, the pressure in the system increases, because as I have told you, when you are dealing with the liquids, again it will increase its density with the temperature, and it certainly depends on your selection of the gauge fluid, that the increment in the length of the expansion of the liquid will be quite linear to give or to get the accurate reading from this type of gauge. On the other hand, you may use when you increase the temperature, the liquid vapor pressure is ultimately increases, and as we know that this type of pressure, this type of temperature measuring devices, their sensing part is made up of the pressure sensing. So when the vapor pressure increases, and which can be easily recorded out by the pressure gauge, and the vapor pressure increment of the liquid should be linear with the temperature, and on that portion of your system you may use them as for their application and to get the accurate reading. And gas is also increased with the temperature increment. So there are three types of pressure spring devices. One in which only liquid is filled and their linear expansion we are monitoring. The second, the vapor pressure, in which the liquid is confined by a vessel, and with that vessel is attached with your bulb. Then the bulb transmitted the heat to the liquid or the gauge fluid. On addition of the heat, in response of that, the gauge fluid vapor pressure arises. And on the other hand, when the vapor pressure of your gauge fluid arises, it will come into contact with the pressure gauge, which is attached at the upper part of the sensor, and that will transmit your reading to the control room, or maybe you will get if you have attached the gauge, so you may take the reading in the field reading part. Then we have gas filled pressure spring thermometer, in which where the constant volume gas is used, and it is a very little tricky, but it's quite simple, and when we will discuss it, you will easily understand the working of this type of sensor as well. This is a liquid filled pressure spring thermometer, which works on the same principle as the liquid on glass thermometer, but the major difference is that it is attached with a burden tube, okay, and when the increment in the liquid linearly with the increment of temperature, what happened, the C tube of the burden tube, the liquid will apply pressure to this tube, and it will straighten with the increment in the length. So in that way it will give you an accurate reading. And then you have a calibrated scale over here. When it is straightened, there is a gear attached with this, so the pointer start to move clockwise in that way, and vice versa. If the temperature decreases, the liquid contracted, on the contraction this C will become more curled, and on curling to this, this gear will move in in clockwise direction. In response of that, this gear where the pointer is attached start to move in anti-clockwise direction. So in that way you may calibrate your this liquid filled pressure spring thermometer. This device has a good linearity. Again, I will say you always try to focus or to optimize your process in a manner that if you are getting any property, linear expansion, volume expansion, vapor pressure expansion, but that expansion or that increment in the property should be linear with the temperature. If it is quite linear, more accurately you can assess, or more accurately the device will give you the reading. If it has certain curves and does not contain a straight line or linear curve, so it will definitely deviate your reading a lot. So it's important that you focus only certain part, like there are certain scales which deviate or give the curving behavior from 0 to 100 degrees centigrade, but beyond 200 to 200 degrees centigrade their linearity is quite linear. Linear expansion property is quite linear. So you only use them in that phase. Although they are temperature sensing devices, but certainly they cannot give you a very accurate reading where their behavior is not linear. Okay, so it's a basic thing to understand before going further in this lecture. Then we have vapor pressure spring thermometer, okay, in which you have a bulb and there is a volatile liquid is at place. And why we use volatile liquid? Because volatile liquid has greater vapor pressure as compared to the non-volatile liquid. The ideology is quite simple, that by the increment of the temperature, what happened, the vapor pressure increases, and the vapor pressure increases. On the other hand, it is attached with your pressure transmitter or pressure gauge, and which is also attached with the calibrated scale, and that will reflect you a very simple reading, and you can easily assess what is the change in temperature occur within the process. So let's see a bit in the paragraph. The bulb is partially filled with the liquid and vapors. Most of the time we can use following gauge fluid: methyl chloride, ethyl alcohol, ether, or toluene. In the system, the lowest operating temperature must be above the boiling point of the liquid. This is another very important point, and the maximum temperature is limited by the critical temperature of the liquid, because beyond the critical point or beyond the critical temperature condition, the liquid exists in supercritical fluid form, where you cannot differentiate the liquid and gaseous state. The temperature pressure characteristic of the vapor pressure thermometer is non-linear, as shown in the figure. Let's see in the next slide what we have. Okay, now the same thing which I was trying to explain you in the previous slide. was that this is the complete vapor pressure of methyl chloride. Okay, as if you see here from 0 degree centigrade to 100 degree centigrade, this curve, this is not a very straight line, or this curve is not a linear curve. Okay, but from, if you going beyond 50 to 55 degrees centigrade, you can clearly see that this curve becomes very linear. So at this part it will give you a very accurate reading, and if you are using it at this part, so certainly it will not give you a very accurate reading, because by the increment of a lot of temperature, there is a very minor change in the vapor pressure. So it's important that if you are using a particular gas fluid, and if you are using certain temperature measuring devices, it will reflect a very linear behavior on the region or on the range of the temperature where your process are supposed to be run, or how much tolerance you will allow for your process. So it is something need to be optimized by a food engineer. Then we have gas filled spring thermometer. The gas filled spring thermometer are something like such as nitrogen, because nitrogen is a very good example of inert gas, and it does not contain a very high intermolecular forces, or you may say its compressibility factor is not high. It is important to take account of that, because here we will utilize the ideal gas equation law in order to determine it. It is a constant volume gas thermometer. Okay, and the pressure of between 1000 to 3350 kilopascal can be measured here, and as I have told you that you have to consider the basic gas laws, and the system are supposed to be run at constant volume. But the main idea is that on the application, or let's suppose the temperature here in where the gas is placed, if here the temperature is increases, ultimately the gas will expand. So here you need to do certain adjustment. So this gauge or temperature measuring device has certain limitations. Let's discuss a bit about its geometry. Okay, most of the time this type of thermometer we will use in laboratory scale, and can be used, but it has certain limitation a lot. Let's start with their working principle. This is the main bulb or environment where or the process where whose temperature you are supposed to be calculate. Okay, it has a very constant volume. This is the calibrated scale, and this volume should come equals to 0 degrees, equals to 0 mark of this scale. Okay, this is the the calibrated scale, as you can see here, P over P naught. What is P over P naught? I will explain you in a bit later. So this is the gauge fluid, and most of the time we use mercury because it has a very high density, it has a non-wetting property, and blah blah things. This is a fixed part, this is another fixed part. On the other hand, you can adjust your column by moving A and B from their places in order to adjust this 0. So what happened this scale is when you are measuring, it will give you the reading of P over P naught. P naught is the initial temperature or the temperature of the water at triple point, and with respect of that it will give you the reading. So the less, I mean the lowest temperature pressure here is will be equals to P naught, and after that the pressure will be rises, okay, because it will place in the water bath. When the pressure rises, so certainly this value will increase in a manner that 1.0, when both pressures are equal, then 1.1 and 1.2, 1.3, 1.4 and 1.5, in that way. Okay, then we have to do some little bit activity on the whiteboard. Just wait. Let's suppose this is a gas filled thermometer, and you can clearly see that this part is a manometer part, okay, through which we can calculate how much pressure changes from initial to final part. So all the categories, subcategories we are studying in pressure spring temperature measuring devices, or in a manner that we are utilizing the linear expansion or volume expansion of the volume expansion property of the gas or liquid, and at the upper part they convert that into pressure indicator, and they are calculated but in a temperature scale. So first of all, I will give you a very little idea about why we so call it as a constant gas volume temperature measuring device. So here let's suppose there is a gas. Most of the time we place N2 here, which has a certain volume, and let's suppose this is the mercury, which is present in this part of the complete YouTube manometer. And these both parts are adjustable, A and B. They are adjustable part, okay. So let's suppose we provide certain heat to this complete water bath, and the temperature here increases in that way, okay. On the increment in this temperature, what happened here, this gas start to expand and its volume certainly increases. Once we reach a certain change, like from 25 to let's say 75 degrees centigrade, when we reach to that change of within the system, what happened, this gas will expand with a certain level in such a manner that it will increase its volume what it was here at 1 to certain part, okay. Now its volume is increases. So after that we have to do certain work. What we have to do is we have to put this P point in upward direction. So what happened, the level of the column will increases, ultimately it compresses the gas, okay. So what we will do, we will elevate this part of the YouTube manometer in a manner, on application of that much, the mercury will reach up to certain height, okay. Here we will get certain reading as well, but the most important thing is that this level will reach to the same mark what we have at the initial position, and the whole thing is filled with mercury. Now here we have a reading in the scale of P over P naught, and through this reading scale we can calculate the temperature of this system. Okay, so I think you can understand that once the pressure increases and how we adjust this pressure by elevating this complete U-tube manometer in upward direction, because it has two flexible part. Okay, we can adjust it from maybe upward and downward. It's according to, depends on the pressure. So now we move towards our derivation side. This is the main working principle of gas filled or constant volume gas filled temperature measuring device. Important thing is that we have to select a very reference point. Reference point where we will nominate the T naught as well, and on the other hand we also place P naught as well. Okay, and here we have selected the triple point as water triple point. If you remember thermodynamics, so for PT diagram we have a triple point here where all the lines are matching each other. So this is the temperature, which is equals to 273.15, where all three phases does exist. On the other hand, the pressure here is P naught, let's say, and as we know that our calibrated scale is either in P over P naught, so we are not interested to know this, because this reading we can easily get from this calibrated scale. So the initial volume, let's say, is V1, and final volume is V2. And if we apply the general gas equation in that measuring device, what happened? P1, V1, T1, or simply you may write here PV over T is equals to P naught V naught over T naught. Well, but at the beginning part of our process, what the initial volume was quite similar what we have in the final volume, because we adjust our complete device in a manner that we can gain the same volume what we have at the initial part. So here we can write that V is equals to V naught. So they both can cancel out. On the other hand, we know that T naught is equals to 273.15. So the desired temperature will be simply equals to, it will go in that way direction, 273.15, but it will give you answer in degrees Celsius. Do remember this. And P over P naught. So you just need to determine this ratio, and by knowing this ratio you can know the temperature of your system. And indirectly you can calibrate that scale into temperature as well, because if you know this scale in this reading, you just need to multiply it with this factor. So it's a constant coefficient, or you may say that constant numeric value. So your scale can be calibrated and directly into the temperature scale is well.